graph of f from the Desmos online graphing calculator. And it looks like we've got points of inflection here and here. It's hard to see, but the graph is actually concave up right there. And then at that point, it turns to concave downward. And we have a relative maximum here. And here's another point of inflection. And here is slope of the tangent line is 0. This is a relative minimum for sure. But it looks like it's actually an absolute minimum, because as the x approaches negative infinity, the function values are getting closer and closer to 16. And as x approaches infinity, the y values are approaching infinity. So there is no absolute maximum, but this is an absolute minimum right here. Question is, how do you figure that out using calculus? So we'll go to board 2. I've already put some of the work here. We want to find the first and second derivatives to help us glean this information. So for this first term, we need to use the product rule. First times the derivative of the second, plus the second function times the derivative of the first. Same deal for this term. First function 4x times the derivative of the second, plus e to the x times the derivative of the first. And then I noticed that every term of this first derivative, of course the derivative of 16 is 0. Every term of this first derivative has an e to the x in it. So I just factored out an e to the x and then collected similar terms. So I've got an x squared, I've got a 2x, and a 4x gives me the 6x and a 4. And we'll later set this first derivative equal to 0 to find the critical numbers. Of course, that first derivative is continuous everywhere. The second derivative, I can use the product rule right here. First times the derivative of the second would be 2x plus 6, plus the second times the derivative of the first. Same deal, there's an e to the x in each term. So I factor out an e to the x and then collect the similar terms that remain from the two polynomials. So I get an x squared and 8x and 10. Setting these first derivative equal to 0 to find the critical numbers. E to the x equals 0 never happens. No matter what value you put in for x, you'll never get a 0. Or x squared plus 6x plus 4 equals 0. And you can use different techniques to solve for these critical numbers. You can use the completing the square and the square root property, or you can use the quadratic formula. Either way, the values, the critical numbers are -3 plus or minus the square root of 5. I estimated those values as about a -0.8 and a -5.2. And I plug numbers in each interval, like I put a -6 in the first derivative, and determine that I'll get a positive result for all numbers to the left of -3 minus the square root of 5. So the original function is increasing on that interval between -5.2 and -0.8 approximately. You could put in, I think I put in like a -4. Found that the first derivative was negative, so that means the tangent lines are going downhill. So the original function is decreasing, and similarly to the right of -3 plus the square root of 5, the function is always, the first derivative is always positive, so the function is increasing. So increasing to decreasing tells me that this is a relative maximum. Decreasing to increasing tells us that this is a relative minimum, but it could be an absolute minimum. Based on the given information, and it's kind of obvious, as x approaches infinity, f approaches infinity, so there is no absolute maximum, but there could be a real absolute minimum, and it turns out this is an absolute minimum. And to find the points of inflection, same deal, set the second derivative equal to 0, and you get points -4 plus or minus the square root of 6. You can determine the sign of the second derivative and the intervals created by those possible points of inflection. And you see that the signs do change. So the function goes concave upward to the left of -4 minus the square root of 6, concave down between -4 minus radical 6 and -4 plus radical 6, and then back to concave up. So indeed, these are points of inflection. And you could actually plug those values back into the original function to get the corresponding y values, which is kind of what I did to get these y values right here for each of these points. Also, I'll make note of the fact that after you've got these critical numbers, you could use the second derivative test instead of drawing this little diagram to determine whether these are maxes or mins. That means plugging the critical numbers into the second derivative and using the sign that is generated to determine whether we've got a max or a min at those points. Okay, hopefully that gives you the idea. I'm also going to include the link to the Desmos graphs in the answer so that you can visit the graph if you want.